Everyone. In this video, we're going to go over the 2009 AP Physics C Mechanics free response question number 3. So the question says, a block of mass m/2 rests on a frictionless horizontal table as shown above. It is connected to one end of a string that passes over a massless pulley and has another block of mass m/2 hanging from its other end. The apparatus is released from rest. So part A says, derive an expression for the speed v of h of the hanging block as a function of the distance d it descends. So we're talking about this block here. It's going to fall at distance d, and we want to find an expression for the velocity of it as it falls this distance. So energy is conserved here. There are no external forces acting on this system. And because of this reason, we can say that the change in potential energy is equal to the change in kinetic energy. That's what this means. Change in U is equal to change in K. So of these two objects, this object is having a change in potential energy because it's the only one that's changing its height. This one's going to stay at the same height, so the potential energy never really changes, so we don't care about that. We only care about this one because it's changing its height. Therefore, we have m1 g of h as the potential energy, half mv squared as the formula for kinetic energy. What I have written here is that the speed of the blocks is vh. This block is going to have the same speed as this one. It's connected by the same string, therefore it's going to move at the same speed. We'll just call it vh since that's what it says in the question. It's given as v of h. So m1 here, m1gh. So as I said before, this block is the only one that has potential energy, or it's changing potential energy. So we can say that m1 is equal to m/2, the mass of this block. m2, both the blocks are moving. So the total mass is m/2 plus m/2, right? So this block, and if you add those two together, you get m. And this block falls a distance t. So when we look back at this equation, we can plug in all the stuff we know. We said that m1 is equal to m/2. We can plug that into here. We have g is just a constant. It's always going to be 9.8 meters per second squared. H is d, as we said, because this one falls a distance d. All of this is equal to half m2v squared. m2 we found was m, so I've plugged that in here as m. And then vh squared, which is what we're trying to find. So if we solve for vh, we're going to get square root of gd. And remember, so g is just gravitational constant, d is how much this thing falls. And in order just to solve for this, you can just take out the halves. M's cancel out too, and then you just square both sides to get vh. Okay, so B. So now it says that now the block and pulley system is replaced by a uniform rope of length L and mass m with one end of the rope hanging slightly over the edge of the frictionless table. The rope is released from rest, and at some time later there's a length y of rope hanging over the edge as shown below. Express your answers to part B, C, and D in terms of y, L, m, and fundamental constants. Okay, so now we've got a rope here hanging off this table. And for part B, we have to determine an expression for the force of gravity on the hanging part of the rope as a function of y. So how much this thing is slipping down, that's y. The general formula for gravity is mg. Fg is always going to be equal to mg. So the problem here is it's not going to be quite straightforward what m is, right? And we know that the rope's mass is m. However, the force of gravity is just going to be what this part is, the mass of just this segment right here. The segment that's fallen a length y. That's how much we're worried about here in terms of m. We can't just plug in this big m here because gravity's not acting on this whole thing. This is all just being balanced by, it's being carried by the normal force, but this, we've got gravity acting on this. It's pulling this thing down. So the goal basically is to find a relationship between the mass of the rope hanging off the edge of the table and the length of the rope that's hanging off the table. So for ropes that are uniform, the mass density is constant, and the mass density is just m/L, right? Because it says it's a uniform rope. And therefore we can just say mass m divided by length L, that this value is always going to be constant. What that means is that we have this segment here falling off this table. Whatever mass this segment is, if we just forget about this part for a second, if we just look at this, whatever mass the segment is, we can just call this small m. And then the length of this is y. So we can just say that whatever the mass this is, if we solve for m here in this equation, we can say that it's m/L times y. Because small m over y is equal to big M over big L. Because the mass density is always going to be constant, right? So if we solve for m, we get this, and then we can plug this value of m back into this equation for gravity, and we'll get that it's f of g is equal to mg over L, all of that times y. So part C says to derive an expression for the work done by gravity on the rope as a function of y, assuming y is initially 0. Okay, so we found out in the last part, this is the force of gravity. Work done is defined by f dot dr, or the integral of f times dr. In this case, it's following a distance y. We're just going to call ry to replace by y. Not a big deal. So the work done is equal to f dy. F we found here was mg over L, all of that times y, and then dy. This is just a basic integral. mg and L are all going to be constants. We can just take that out of the integral. We've got y dy. If we take the integral of this, we can just add, so the exponent here is 1, so we can just add another 1 to this exponent, y squared over 2. You just solve this integral. It says plus c, but it says that we can assume that y is initially 0, which means that there's not going to be any plus c here. We can find that if you plug in at y, at any time t, or at time is equal to 0, y is equal to 0. So c is generally there for whatever the position was at time t is equal to 0. And since the position is 0, we can ignore this. So work done can just be written as this equation right here, mg over L times y squared over 2. Or, as written more simply, mg y squared over 2L. So D says to derive an expression for the speed Vr of the rope as a function of y. So by definition, work is equal to the change in kinetic energy, which is equal to half mv squared. So here, in general, you'd say, like, where's the other term, like half mv initial square? Since it starts from rest, we're not worried about that. We're just worried about the final velocity. The initial kinetic energy is considered 0 here. We're worried about the final kinetic energy, since that's what basically ends up being the change in kinetic energy. So we found an expression for W here. We can plug that into here. Kinetic energy is just half mv squared, as I wrote right there. We don't have to do anything to that. We can solve for Vr. We can take out the 2, the halves, those cancel out. We can bring the m over. The n, this small n, is the same as this big M, so we can just cancel those out, because that's the mass of the rope. And then we can just solve for Vr, and that's going to be equal to square root of g over L times y. And remember, this y is supposed to be outside of the square root. That's what it's trying to say by these parentheses. That's outside of the square root. But if you want to bring it back inside the square root, you can just say the square root of g y squared over L. And all I'm doing is bringing this inside. This is going to kind of help, I guess, for part E. The hanging block and the right end of the rope are each allowed to fall a distance L, which is the length of the rope. So the string is long enough that the sliding block does not hit the pulley, so indicate whether VH from part A or VR from part D is greater after the block and the end of the rope have traveled this distance. So now we're looking at both of these situations here. That's why I have these pictures here. So we're looking at this thing falling, and this one's also falling down. So which speed is greater after distance L? Well, we have this equation for VR here. That's the equation of the velocity of the rope, and so I've written that here. We found in a previous part that VH is equal to square root of GD, which is equal, if you plug in L into both of these equations, this will be equal to square root of G times L. In this, if you plug in L here, it's L squared over L, it's just L square root of G times L, so this whole thing is square root of GL. These things are the same, therefore the speeds are equal after the travel distance L. That's what you have to do with these equations, and the one that we found in part B, or A, one of those parts, I think we found it, so we found in part A, VH is equal to square root of GD, so you just bring that over here and use it and plug in the values, and you'll find that the speeds are equal. So that's the end of this video. Thank you for watching.